the reason for season? What causes season? So we're going to take a look here and try to answer that question for you so you have a better understanding how seasons occur. We're looking at the Earth going around the Sun in 365 days. It's also known as 1 year. All planets make an orbit around the Sun. And as it goes around the Sun, we know that various latitude we get different daylight amount of daylight in each latitude, different lengths of time. So why some areas get more light in the summer and less in the winter, and vice versa. Another way to look at this is we look at the orbit, first of all. And we have all the planets go around the Sun in kind of clockwise direction, looking from the north. Could this be the source of our season? That this going around the Sun is causing the season? Not exactly. Let's take a look at the Earth's orbit. You look at the orbit, it's not a perfect circle. There are 2 points in time that the Earth is at its closest and furthest distance away from the Sun. The average distance between the Earth and the Sun is about 93 million miles. In January, there's a term called Aphelion. That's when the Earth is at its closest distance, or furthest distance, actually, away from the Sun. It's about 94.5 million miles away. That's in January. And then in July, it's called Perihelion. The Earth is about 91.3 million miles. So the orbit's kind of a squish. And all planets that orbit around the Sun have a kind of an elliptical orbit. Okay, so it's a little bit like a circle, but a squish. But that doesn't affect the season or the amount of daylight that we receive on each of the planet or here on Earth. Let me show you now what we mean by the Earth tilt. We looked at the orbit, and as it goes around the Sun, we have the season. The equinox is both north and south pole are equal distance to the Sun. And then 12-hour days and 12-hour nights. Then we have the vernal equinox and the autumnal equinox. Then we have the summer solstice when the North Pole is leaning toward the Sun. And then in the winter, we have the winter solstice. That's when the North Pole is leaning away from the Sun. But in all cases, you can see that the axis on the Earth is in the same angle and position pointing up. So it's tilted at 23.5 degrees. It's not straight up and down. If it was straight up and down, we would have continuous equinox. Okay, so here is another model I want to show you that we have the Earth going around the Sun. That's called revolution. Down here we have the Earth. This is an actual satellite image of the Earth. The dividing line between day and night is called terminator. Okay, but that doesn't cause the season. And then over here we have the Earth going around the Sun, and the North Pole is pointing right at Polaris, which is our North Star. Okay? And even there you can see the Sun bobbing up and down. Okay? So those are a few terms to understand that we have revolution, which is the orbit of the planet around the Sun. Now let's take a look at a view from Portland. Okay? From our location, the Sun is 45 degrees above the horizon. That means we're 45 degrees from the equinox, but the equator. Okay? Here is the Earth, and on the day of the equinox, the Sun is directly over the equator. And there's that red dot is us, Portland. Okay? And on the equinoxes, we have about 12-hour days. That's 12-hour days throughout the world, including Portland. Okay? So from our location, the highest point is at 45 degrees above the southern horizon. If we move forward, you'll notice that the Sun would set directly in the west. Okay? And then, as we go through the night, we get 12-hour nights. And then coming up on sunrise, we'll see that the sun rises directly from the east. And then it will reach its highest point at 45 degrees at noon. And that's for the equinoxes. Okay, then down in the southern hemisphere, they also have equinoxes. And here we are, the summer solstice. The summer solstice, now we have 45 degrees. It's our location. At 23.5 degrees, you get 68. At that point in time, the sun is directly over what we call the Tropic of Cancer. That means the sun is in Cancer. Okay? And then up here, the Arctic Circle, right up there. And that's exactly where the terminator line, right at that conjunction. And that's why up in the north they have 24 hours of daylight, and the opposite down below in the southern hemisphere. Okay? So on the summer solstice, we have the highest point of the year, and the sun had roughly 16 hours of daylight. And that's why temperatures should be much warmer in the summer than it is in the winter. Okay? And we also have seen that the sun set much further up in the northwest, and then we get our shortest night of the year, and then we get northeast rise of the sun, and it's back at 68 degrees. In the southern hemisphere, it's opposite. They're getting their shortest day and longest night. Now we're at the winter solstice, and that occurs in December. And here we have 45 degrees, subtract 23.5, you get about roughly 21, 22 degrees. And that's at its highest point in the southern part of the sky. And this one we have only about it's under 9 hours of daylight, and we have our longest night of the year. At that point in time, the sun is directly over what we called the Tropic of Capricorn. Okay? And so that's that line right there, Tropic of Capricorn. And down in the southern hemisphere, they're getting our longest day and shortest night. Up here, we're getting our shortest day and longest night. And look at the Arctic Circle. Again, that boundary, the terminator, marked the line. So the sun is at its lowest in a very short time. They heat the air above the ground. And that's why we experience much cooler weather in the wintertime, and then the vice versa. And then we have our longest night of the year. And that's why, quite often, during the holidays, people celebrate return of the light with Christmas lights and candles. And then we're back to 23 degrees. So, talk about analemma. If you go forward, you notice that we kept the sun at noon. It makes kind of a figure 8 pattern. Okay? Goes back to the lowest point that we just saw. And then we have 45 degrees. That's where it keeps crossing. Then it goes up to 68 degrees. And so we kind of make the figure 8. And the reason it leans off the line a little bit is just the way that the Earth is making its way around the sun. I want to show you this. Here we have in June for the summer solstice. Okay, the sun is at 68 degrees at its highest point. It has a much more concentrated point of light to concentrate the air above the ground and heat it up. Where in December, the sun is at its lowest angle and the light is more spread. And it has only about 9 hours of daylight. So it had really no chance to heat up the air above the ground, where in the summertime, it had much more chance. So up here, we can see again that the Earth is tilted 23.5 degrees. That's why we have these lines on the globes and such that marks a certain point that's affected by the season. Right? And we have the equator on the equinox. The sun is directly over the equator. And then we have Tropic of Cancer and Capricorn, which the reason they're called Cancer and Capricorn is that the sun is in that constellation on the particular point of time. And then Arctic Circle is defined by the boundary of the terminator, right, between day and night. And then that's what marks that line up on the globe. So a lot of people didn't realize it's because of the Earth tilt that it marks those lines on the globe that you see. Okay? And around the world, there's certain monuments at each location that have a marking that shows when the sun is directly overhead. Now let's take a look at this. We're at the Berlin Equinox in March. This is the equator. This is 45 degrees north. This is us, 45 degrees south, and then south and north pole. Okay. Now remember, in the southern hemisphere, the sun is actually in the north, where in the northern hemisphere it's actually in the south, and at the equator the sun is directly overhead at the equinox, and then both north and south pole. Okay, the sun is going to be right along the horizon. Okay? So this is kind of fun to see and watch what happened to the amount of daylight that we see in the different hemisphere. Okay? So let's take a look here. If we go forward, then we'll see that both the 45 degrees north and 45 degrees south, they're going to be about the 12-hour days and 12-hour nights. And then at the equator, it's going to be about 12 hours as well. And then up in the north and south pole, right, you get continuous sunrise and sunset. Right? So here we are going into the night. They're both about the same. Both the north and south pole, but still a kind of a twilight. Right? And then here we come back up to sunrise. It's back. The sun is at 45 degrees north, 45 degrees south, and there's the sun directly overhead. That's when you have no shadow on that day. Now we're at the summer solstice in June. Okay? Here's Portland, 68, and then down in the southern hemisphere, it's the opposite. Okay? The sun is lower. And then we have the over here, the equator. This is the North Pole, and this is the South Pole. South Pole, dark, right? And North Pole, all light. So you'll see the sun seems to be making a continuous daylight, down in the south, continuous night. Okay? Then on the north here, we're going to get our longest day and shortest night. In the south, they're going to have the shortest day and longest night. And at the equator, well, it's just about close, almost even. Right? So let's go forward, and we can actually see that. Right? Where we see up in Portland, we get the longest daylight of the year. And then the temperature is much warmer at that time. And so we go forward, and then we see in the south it's already dark. In the north, now it gets dark. In the North Pole, still daylight. In the South Pole, it's dark. Right, so back over here, right, the day starts again. In the south, it's short. And then we have the equator, just another kind of half and half day. Okay, so that's fun to see. And now with the winter solstice, the opposite. Okay, here in Portland, we'll get our shortest day and longest night. At the equator, okay, another long day. North, all dark at night, and the south, all day. So the opposite from what we just saw. Okay? And so the color represents the ring that we see in the profile. Okay? So what we'll see once we get going forward, that in the south, okay, they're going to have long days. In the north, we will have our shortest day of the year. And so it's always have to remember that in the southern hemisphere, the sun and the ecliptic are seen in the northern part of the sky, kind of the vice versa. And so people tend to forget that. So let's take a look here. As we go forward, then we'll see that. Right? And so here Portland, it's already at nightfall. in the southern hemisphere, still daylight. Now they're getting nightfall. Right? And so we will see down in the southern part of the sky, it will come up daylight first. Portland will come follow later. And there's the equator. Down at the north, up at the North Pole till nightfall. And then up in the south, you get continuous daylight. So those are fun to see. Now, we're not the only planet with the tilt. Here's the 9 planets, okay? And we're looking at the rotation. Rotation is the day, amount of days. So Jupiter had 10 hours. Earth had 24. Mars just a little less. But these numbers represent the tilt of each of the planets. So we have Mercury, 0. Venus is upside down, almost 180. 23.5 degrees for the Earth. Almost identical for Mars. Jupiter, pretty much almost straight up and down. Saturn wobbles at a 27-degree tilt. Uranus spins sideways. And then we have Neptune, a steep 30 degrees. And Pluto is almost upside down. So you can see each planet has a different amount of degree of tilt. Okay? And they all have season. Jupiter not so much, only 3 degrees. Okay? So all planets, and Mercury, all planets experience seasons. And that's all because of the tilt. So the answer to the question, what causes season? It's the tilt of the Earth. Let me show you this satellite imagery of the Earth. You notice up in the northern hemisphere how the glaciers or the snow keep going back and forth, back and forth. And that's another clear indication how the Earth is tilted. And if we go around the sun, we see the weather, the change. And especially in this radar image, photograph, that we see that the snow. Now on Mars, it's the same thing. Mars goes through season. And here's the actual image of Mars going through spring, that we can see the north and south. In this summer, okay, just like here, we see an increased size of the glaciers. And then in fall, the equinox. And then what you're about to see is a giant dust storm, okay, that's covering the planet. Okay? And so we can see, just like on Earth, we see the season. Okay, so we wrap this up. And what causes season? It's the tilt. It's not the orbit or the revolution that the planet makes around the sun that causes the season. It's actually the tilt.